I want to just use this slides quickly summarize what we done for Turing machine, that topic. I do remember some place I run a little bit rush, maybe jumped over a couple of topics. And so let me just, I just summarize a few things here. Just in case anybody interested in any particular aspect, you can go to our either booklet or go to internet, find some more information to have a look around. First of all, we learned something we call Turing machine. We should be able, the learning outcome for that 2 weeks is students should be able to construct a simple Turing machine to solve any particular, well, not very large, some small problems. As the exercise we done tutorial, that kind of question, yeah, if I gave you a small task, you should be able quickly just draw a diagram. That's something I hope everybody can conquer that. Then another thing is the concept of universal Turing machine. I have to say this is something I do remember. I skipped that during that lecture because the time is short. Let me just use this opportunity quickly, just say something about this. What we've done so far is to define a particular Turing machine, design diagram, draw something that is to particularly achieve some function, certain function. That is not universal Turing machine, okay? Then what the universal Turing machine means is we have generic Turing machine, and let us to input your design. So if you design Turing machine, a particular Turing machine, somehow you can write down your table. We have a table, yeah, Turing machine. Instead of drawing diagram, you can write as a transition table. So you can imagine transition table, after all, is just a sequence of those informations. Yeah, this transition. We can somehow write them down on the tape. So now, that's Alan Turing's proposal. Yeah, imagine we add extra tape. From our traditional Turing machine, small machine, only have one tape. So let's say we add another tape. Then that tape will record your design, your transition table. And then we add a little bit more functionality, or maybe something to allow this special Turing machine can always go back to look up for the extra tape, find out your transition, and to run whatever you just designed. So can you get it? This is just a break the idea, bring any hardware design into software. Imagine your transition table is actually, we done transition table, we think that we implement as hardware, as machine, but now you change it into tape, okay? And then you have universal hardware, which is universal Turing machine, which can read your tape and do things accordingly. So that is really brilliant. The first that not necessarily first, but it's a very early stage. We propose this idea. We separate, we bring hardware into software, right down into a tape, and then we have a generic machine, generic piece of hardware to run everything. So that's why it's called universal. Okay, universal Turing machine. This concept I remember I skipped it, so let me just quickly summarize here. Okay, if you're interested in it, you can Google it to learn a little bit more on that. So then everybody should accept this saying. We treat Turing machines as have the same power as these days modern computers. So they are equivalent, okay, in terms of the functionality. Well, the power it can achieve. That's simply because we can build software on top of that, the model. That everything computer can do, then we can always program it and to let it to compete, whatever the computer's power. Okay, so we quickly introduce this holding problem. That's what we want to try to prove that there are something really unsolvable. That's what we done last week. So really, now go back to that is the initial motivation why this Turing machines concept was invented, was created. The idea back to those days is want to prove something is computable or something is not computable. That is the original idea. It's not even just for solving some, data crunching, some big problem, try to speed up our human labor, the efficiency. It's a purely mathematical problem. Yeah, so just want to say, if we have a good model to help us to identify some problem is solvable, computable, or some problems is not solvable or not computable. So that's really start from that point. So it sounds a little bit like maybe you probably never heard this. So it's nice to know this piece of history, how the things evolved, how things come to these days. Now we have computer everywhere. Yeah, so you can't imagine your life without computer. Anyway, so that's a little bit summarize really learning outcome. Rather than talking about those history things, understand what the Turing machine, how it come along. Rather than that, I just hope everybody have this sense of ability, should be able to have this kind of ability, which is anybody give you a couple of basic functionalities, then you should be able to quickly learn that, understand what that function can achieve, and then from there you can build your program to solve more complicated, more harder problems. So that is that kind of ability, problem-solving ability, and then lead you to become a good programmer. Yeah, not really good. If I say program, it's a bit too low level. Really, we want you guys to be able to design good algorithm. Okay, that's really nice thing. The good algorithm is something you have to figure out a way to solve problems. Yeah, and then really programmer will implement your algorithm. Yeah, so design good algorithm. That is something we should learn. That's of course that you can't learn that in 1 day, 2 days. So you need good period of time to get used to it, and then I think that really require your good ability of generalization. So when you say problem, how to generalize the problem, and create a good idea, say how you go about to solve it, and then write it down into step instructions. Okay, that kind of ability is good. It's good to use the Turing machine as a model, as a basic model to practice on that. Okay, then the problem like I gave you in worksheet 4, maybe most of you haven't looked at it yet. I think I explained last week a little bit. It's kind of the same motivation. I want to force you guys try to train yourself to solve problem from basic. Okay, from very basic, and then you work out a way to solve problem. Okay, so let's just finish that. Move on. Well, today's topic is not only today and next week as well. We will need 2 weeks. We're talking something called induction and recursions. Okay, so you probably heard the word recursion. Is kind of a special term, has this special meaning. Leave that alone. We don't talk about recursion yet. Just talking about induction. In our normal everyday life, we use the words of induction. Normally used to mean, like say I run an event, I call this as induction event. Or when you join university, back to last September, we schedule you, say you have induction week. Okay, so that's the meaning of induction, is we get a newcomer together, we introduce something about the university, about your course. Or if you join company, they tell you the company's history, tell you how you go about to do things, like that. That is what we mean by induction. Okay, but here it has totally different meaning. It has got his, well, really, his meaning is not really just run an induction event. Let me just explain what does the induction mean. I actually today, on my way to work to here, I was thinking induction. Sorry, I'll just jump a little bit. Induction translate into Chinese. I'm not sure how many Chinese, do I have any Chinese students here? If you translate into Chinese, it translates into two words, and one first word means you forward, go forward. Okay, that's one. Second word means generalization. So basically, the induction means you moving along, yeah, going forward, and then generalize your steps. So that is exactly the really induction meaning. We try to work out a method to generalize every step what exactly you're doing. We're not saying step 1 do this, step 2 do this, step 3 do this. You might find every step they're doing same thing, similar thing, just changing the slight different position, and you do same thing. Okay, so that's really the meaning of induction. Okay, so like just go back to something else, totally out of computer science, which is like religious stuff. So let's just ask you a question. Assume we know Eve was a human being. Yeah, so Eve was the first. So assume we all believe in God. Doesn't matter if you don't. This is just an example. Yeah. So if we imagine human being really follow Bible story, your Adam and Eve, they create, well, eventually they are first parents. Then from there, you get generation down. Yeah. So you can say, okay, we will say, we can declare, we make a logical statement saying Eve was human being. And then you can also, this is second line. Second line here is kind of a generalization. It's a human mothers. So now we're not talking about Eve, we're not talking about Eve's daughter or daughter's granddaughter or something. We're just talking about for any human mother. So that could be anything, put it just like a variable, yeah? A variable X, as long as X is a human mother, and if she produce offspring, then that's all human being. Okay, so what we're trying to do, you can tell this is a kind of definition. Yeah, although it's just saying in a sentence. What it gave you is it gave you the very first human being, human mother, yeah? And then from there, then they just generalize the step. Say how is next generation can be produced. It's just, as long as you're a human mother, then you produce children, they're all also human. So it's a human mother produce human. This all going down, yeah. Of course, here we didn't talk about father. Anyway, just the example, yeah. So now, question is, if say Noah was Eve's great, and 8 generations down grandson. Actually, I don't know the story. Yeah, so this is just saying like that. So can you prove? How can we prove Noah was human? Yeah. Then we just use our brain thinking, oh yeah, based on you already said, as long as from that rule, yeah, from second rule, you can really. This is actually called inductively reasoning. You can go down step by step. You go 8 generations, and so 8 generations down. So you can say, you can prove, say, if Eve's daughter or son, or Eve's daughter is human being, and then married somebody, and have another one, go down eventually. Then you can prove that Noah is human being. Okay, so really. This is just showing what do we mean by induction. Is you give a generalized step, and then you can really from step to generate your mathematical proof. You can really prove by using that rule. Yeah, not only just prove one particular instance. You can prove entire whole the offspring for this family. Yeah, they're all human being. Okay, so it sounds like I'm not sure if it is really good example. The people don't believe in Bible might feel a little bit offended. Anyway, so now let me just give you another example. Probably this is better. Imagine you try to climb up the ladder. You try to learn, try to do the climb up ladder. And we know when you climb up ladder, each step they have equal space, and the technique required to climb up is the same. The skill, skill, you just go up. And so really is if you can do one step, provided you have enough energy. If you can do one step, and then you can carry on, then you can prove yourself. You can go, you can climb up, whatever how high you can reach. But then the first step maybe need some special thing. We don't know how high it is, or maybe the condition is slightly different. So really, the first step, we can treat it as separate. So therefore, we just need to demonstrate you have ability, you can reach first rung. And then you can also carry on to show that you have ability to get from one step to another. So really from this step to another step, this is something in the middle, could be anywhere. If you can prove you can do that, then you can declare you can go anywhere. Are you with me? So you don't have to say, I can do the first step and climb second step, third step, you can't do that. You just say, as long as you can do a particular step, show how you move from particular step to the next step. Are you with me? So this is something we call it induction. We call it inductive definition, actually, or inductive proof. There's two ways, either define things or prove things. Another example here, I got the picture from Wikipedia, and it says it's good. It's also a good example. Is that formal description for mathematical induction can be illustrated by reference to sequential effect of falling dominoes. So you have dominoes all the way along. So each domino, they have same weight, and they have different distance between them. They're all equal, So if one fall, and then coming on the differently 100%, they will just fall forever. You just need an initial push, and then they will go for all one by one, step by step. So never stop. Okay, so now let's just summarize this. We just talk about now induction. Now we treat it as this is a mathematical, I would say methodology, or maybe just don't put it that high word, just method. It's a method. We use it in maths and in computer science and this kind of area. So what we do is we need a basic case. And now we're in a situation we try to define something. We want to make clear this concept. What do you mean by this concept? So when I try to define this concept, what I do is I gave first the base case. Just like I said, Eve is a human being, is a human mother. Okay, so that is the first, that's my ground. So the first incident of that thing you try to design. So make sure that is really your base case. And then you will run this, we call it inductive step. You can assume something it's already defined things there, and you tell me from there, how can you generate a new one? Okay, so go back to Adam, Eve example. It just said as long as you're human mother, you produce offspring is also human. So that kind of is just tell us inductive. That is inductive step. Tell you what's the next thing come along. What rule is there? Like climbing a ladder is you all just say how can you climb from current step. You don't say which step. You can say step n, and then how to move from n to n plus 1. So really is from n to n plus 1. This is something, if you can work out how to do this, and done. okay? And lastly, there's something we call the exclusivity, which is you have to say, you have to declare, basically that's the meaning in this induction is only those things you define from the base case and the inductive steps are legal. So when you try to say you define something or you want to do something, anything you can generate is based from your inductive step, okay? Otherwise, if you can't be generous, anything they say, you can't generate from your inductive step, which would be not part of your definition, okay? I will show you later. Now, maybe still go back to human being, yeah? So if you pick up something, this object or this entity is not cannot be produced by using that two rules, then that is not human being. Okay, so we only talk about something generated by the above two rules. So that's called exclusivity. And because this is applied for every inductive definition, and really just save us time. You don't have to always mention, you don't have to say always mention that one it's in or not in. So we just assume, yeah, we know this exclusivity is in it, okay? Probably it's better now give you some more concrete example, more easy to make sense, and using numbers, using maths example. Natural number, we all know, it has got infinite growth, the bigger number, so it's infinite. How you properly mathematically define what do we mean by natural number? And here is a solution. We can use our induction method, which you just said. You just say, okay, what's the basis? We know is we start from 0, okay? It never go down, don't have a negation. And we just simply say, okay, our base case is we just say 0. Yeah, I declare 0 is a natural number. And from there, you can just give a generalized rule of the natural number. Then we know the distance, the difference between any two natural numbers is 1. So you pick up any number. If it is natural number, it's guaranteed you plus it by 1. Next, that will be next natural number, right? So we just say if x is already a natural number, so now you have to be careful now. We didn't say 3, 4, 5. Yeah, we just say generic anything x. As long as x it is natural number, we just say so is x plus 1. Then sometimes you might argue, say, all of a sudden you just jump to x. So what is x? It's just like a little bit bizarre. Where is this come from? Then I tell you that. Don't worry. X, just assume. If you can prove x is a natural number, you might ask how. Don't worry, because we have a base. We start from 0. Yeah. So if you want to use these two rules to generate all the more numbers, you can simply start from 0 and apply this inductive rule. You can say, okay, 0 is natural number, right? You told me 0 is, and I do 0 plus 1, then I will get a second one. 1 is also a natural number. So now you got your set is getting bigger and bigger. Now you can take 1 and plus by 1, again you get 2. Yeah. So you already proved the 2 is also a natural number simply because I know 1 is natural number and 1 plus 1 is 2, and you get 2 and plus 1 and 3, etc., etc. So you never end it. You never have a problem with picking up the x. Yeah. So that means anything if you already proved that's a natural number, then we are telling you, no worry, you plus by 1. Here again is another natural number. Okay. So then we want to say, okay, exclusivity is only numbers generated by using another above two rules, they are natural number. So if you gave me something like 3.4, I can again say if you say this is natural number, you have to prove how can you generate this start from 0. Yeah, you give in 0, then you will prove that 0 plus 1 plus 1, you never reach 3.4. Okay, so therefore 3.4 is not natural number, so it's not. Yeah, there's another definition. Examples for the induction method. This just show you inductive rule can be more than one. So far, that we use the human being example, proves with human, and we do the climbing up ladder. Then we just looks like induction just one rules. But normally you're allowed to have more than one rules. So here's the example. We don't have to go too very deep on the meaning, but we're just telling you, if you recall, we introduced something called the regular language. Regular languages represent, a language can be represented by a finite automata. If you recall, we learned that, yeah. So if you can draw a finite automata to represent this language, we will say that's irregular. That is so far we're telling you. Now I can give you precise mathematical inductive definition for a regular language. So here is the regular definition. For the basis, the definition, we will just say any language. So you can see this means any language have only one value, only this value in it. Only say let's call it A, and could basically that means could be anything, any little thing in the one element in the set. We declare that is regular, because there's no other rules. You just gave me concrete values. You're saying that is language, then it's so simple. So that's our base case. That's our start point. And from there, inductive rules is if A is already regular language, then you can do A star. So A star means, write down here. So what the definition here is, you have empty, then you have A itself, and you have A2. A product two A's linked together, and 3X linked together, 4A linked together, etc., etc. Infinite go up. Okay, so if you started from a 1A, and then the A star means from empty and A, any number of A's. But if you start with, that's a start with A. That's one rule. And I give you another choice to generate a more complicated language, is if you have two languages, both are regular language, A and B, and then it's guaranteed you run a union operation between these two, so they are still regular. So these rules are saying, give me regular language, you do a union operation, and also this is another operation, do the production. So this here we already done production, yeah. So you just concatenate two strings from two languages, you generate a new sentence. They are still regular, okay? And they might have some other rules they didn't bother to mention. Anyway, those are just example from our booklet. You can see that the way I'm building up, what do I mean by regulation? Regular language is to give you a very basic one and tell you from there what rule, what operation you can apply, then the things you generate is guaranteed they're still regular language. Okay, and you can see from these rules, you will never ever to generate a rules string like if you have things like this, with the brackets. With brackets, this thing because you started from individual element, you don't have a concept of pairing up. Okay, so it doesn't matter you do union or you do we're not talking about union production, and you will never ever generate a string like this. So this is really the old regular language. Okay. Anyway, so after all, this is just example. Okay, by using this definition, well, by using this method, I have to say, you can actually check, just convince yourself. Yeah. So if I gave you a set of language, for example, this is the language I'm giving you, can you prove, convince yourself this is regular language or not? What you can do is using based on definition I gave you, you can check all the string I gave you, check themselves if it is can be composed from a basic. So really you can start from basic. You have a set of A and set of B. They both by definition, by using our base case, they are regular. They are regular language, so no doubt about it. And from there you just say, okay, because A and B is already regular, and it's guaranteed you have any number of A's and any number of B's, they're also regular, right? Then you can also do the, because they're all regular, then you can do any number of A's followed by B, or any number of B's followed by A, yeah, by using that rule. Previously I have a lot of rules. And then you can also say, yeah, so this one, this formula I actually represent this set. Okay, this set saying any number of A's followed by one B, and this is any number of B's followed by one A. Okay, then you apply a union operator. You just put them together, and this is set we're talking about. Okay, so you can have A, B, a lot of B's. So this is just showing this is all regular. And this method is doing. You can do either top down, or you can start from here, bottom up. It doesn't matter which method, as long as you can give the precise step, showing that every step you're using that inductive rules. Okay. So anyway, so I think the most important. Okay, let me just still have more examples. Just try to give you more and more examples. You realize in the real world, really induction happen everywhere. Okay, so let's just talk about palindrome. Yeah, to be honest, there's a lot. Not everything. They can be defined inductively, can be generated inductively, but a lot of them, most of them, yeah. If you observe a lot of real things, you find they follow the inductive rules. Okay, let's talk about palindrome. So palindrome is a string, it's a symmetry. Okay, symmetry string. You read it left to right and right to left, it's the exactly same thing. And then be aware that palindrome can be like this, Hannah, is even number of lengths is exactly symmetry half, but it does allow to have things like this radar. So you have a one out thing in the middle, yeah, and then rest of thing they're all symmetry. That's also allowed, like this one did. So you have a D I in the middle, but both ends are D, and even finally the empty string is palindrome, because empty doesn't matter you read it from left or right, right to left, it's just empty. Okay, so let's give you an idea. If you try to describe palindrome using induction, the empty string here should be our start point. Yeah, agreed. The empty is the shortest palindrome. Therefore, so we have this first definition. You just say, okay, I'm telling you what do we exactly mean palindrome. Rather than saying read it left to right, right to left, is the same way. That is too not very precise definition. No good. It's just a natural language. I'm using mathematical language to define that. I will just say, look, if you gave me something empty, the empty string, then I know that is a palindrome. No doubt. Yeah, so that's my first example of palindrome. And so actually now you can say there's Hannah, so the empty string is the palindrome, but I have another start point. Another basic example is a single character. So if you gave me A just B or C. Any single character is also palindrome, right? So we are allowed to give you more than one base case. Yeah, in real different depends on situation. In this case, we have another base case, so the two together. And then induction, our induction rule is, again, you see, we suddenly jump to something we don't know. Just refer to as a P, okay? So as long as P is already a palindrome, and we just say, so is X on this end, and also on the other end. Okay, and where X can be any character in your alphabet. So are you happy with this definition? So then we will say this is induction. Okay, then I think if you're giving, let's say if I want to define palindrome, if you're using this method at the top, then it's okay. Yeah, everybody understand. Yeah, so what do you mean? But then this way, then the bottom, that's a proper mathematical definition or good way to define it, and then it is this is what we called induction. Okay, we have spent more than half an hour now just talk about induction. Yeah, that's all old examples about induction. So I hope you guys got idea. Yeah, okay, let's move more examples. Sorry, I hope we haven't fed up, but then this, I have to tell you, this is really useful for everything when you write program later on, when you try to design new algorithms, thinking something, solving problems. Yeah, in AI, there's a lot of problem solving challenges. It's always good to using this technique, thinking, okay, I want to solve this problem. How can I start the first step, the very first step, what I need? And then you can suddenly jump to, if I already solved this problem in this stage, how can we move forward? Okay, that's really a good way to train your brain to think things, to go about solve problem. This is generic method, okay? So anyway, so here this is actually relevant to computer science very closely. Then we know we have graph. We learned last semester. We learned what do we mean the graph, and graph consists of a lot of vertices, and then joined by what is called edges or arc. Yeah. So when we generate the graph like this, you can define, that is we need to define what do we mean by a path. Yeah. So let's say I have a concept. I want to say define what is a path from A to B in a graph. And you might say, oh, that's path is you can go through. Yeah. If you can go through, that's a common people interpretation. You can go through from this dot, go to the other one. There is not all the joint. Yeah, so that is not very precise definition. So real definition is like this. At the bottom, I write down. This is the proper inductive definition for defining what you mean by path. So here, the first line is saying there is an arc. Okay, so if you, let's say you use here, like in what is it, C, and there is an arc. Yes, there is an arc, and between A and D, they are direct neighbor. Yeah, so you can hop from C to D by one transition. Then we can declare there is a path. We say the path exists. Yeah, so path exists between A and B as long as there's an arc between them. Yeah, so there is nothing to need to be proved, because you can see, use your naked eye, you can see there's a direct link. Yeah, but then from there, next thing is very, very important. You suddenly jump to say, right, as long as there is an arc between A to some node, there's A to C. So they have one arc from there. And then they say, and there's a condition and there's another path start from C to B. So like this, this graph yeah, I can do say, I say it's from A. If you can prove that A to B, let's call it B, yeah, so that is B. So there is a path between A to B, but then I suddenly say, okay, is a path to another place? I don't know, maybe somewhere else. And you don't have to prove them step by step. You just say, there is a path. As long as somebody already tell you, they proved there's a path between C to, from C to D, C to B or C to D, whatever is the third position. So let me just quickly draw it here. So this is one place, and you if you can prove A to B, yeah, so A to B, and then rest of thing, really, I don't know. It's just somebody tell you you already proved from A to B and C to, there's a path from, yeah, let's call it to C, yeah. I think the meaning probably label the variable here is not very good. So as long as you can prove, let me just say it in my way, yeah. So if there is a path between that the dotted path, really you're not interested in what's underneath, but if you know there is a path, okay, and then you can prove then between A to C you can link them, yeah. It's just like if you're buying ticket to fly like from here to New York, and if you know there's direct fly to there, yeah, direct go to New York, that means there is an arc in your graph. Then they're saying from Bristol you can go New York. Then you can say, okay, there is a path from here to go to New York. But then if you are told from New York can go, well, this is from Bristol, yeah. But then if you know, actually from Bristol to New York, there are no direct line, yeah. But there is a direct link from Bristol to London, for example. And then people tell you from London you can directly fly to New York. If you have these two information, then you can prove that, okay, I can definitely buy flight. After you have some stops, but I can go to New York, yeah, because you know from Bristol the direct flight to London, it's too short, yeah, from to London, and from London you don't really care how many stops, as people already tell you, you can fly to New York from London, okay. So this is the example we use inductive definition to give us definition on the finding path, and then you know giving graph. Finding path is most these days, yeah. You have on the route finding algorithm, yeah. So you have GPS, and you have your app on your car, or on your phone, and tell you from here how to find another place. In that kind of algorithm, underneath every step is using induction, okay. Is from here, find the next one, from next one, how to optimize, find another one. So it's everywhere, okay? So really finding paths on the graph is heavily used algorithm within computer science. Okay, so now, yeah, we want to convince you. We spend long time using many examples, show you what we mean by induction. You might wondering why we learn this, why it's important. And the first thing is I think as a computer scientist, I want to say, and okay, so using induction is good for our programming things. One thing is how can you, if you want to prove your program, say can stop, yeah, back to a halting problem, but now we're giving individual concrete program. How can you mathematically prove that piece of thing will not fall in a loop? You can use induction. Using induction to prove what condition this program can stop. So let me see. So it says, okay, where is that program? Yeah, here. So this is the program I gave you. I just quickly have a look what it does. It starts from initialize a variable as to 0, and I run the function code. Say get positive integer. So we don't know what is that, how they do. That will return an integer for you. And then here is the loop. There's checking if value is 0 or not. And then we probably notice this. Okay, so the above line is not relevant because of the stop condition is checking if v is not 0. If it's not 0, it will continue loop. So only one v down to 0 will stop. Okay, so we use our common sense. We can see provide this function correctly, return your positive number, and here you're just counting down. You should stop. Okay, you should stop. But we can mathematically prove it by what we do. We just say it stops. This inductive stop is saying if we can suddenly assume your program stop when at n is any arbitrary number, integer. You can prove that n can be eventually go down to 0, can stop, and then you can prove from there. You can prove if n works, n plus 1 also works. Yeah, because n and between n and n plus 1, just another one loop here. Yeah, you go down that will from n down to n minus 1. Also the base case, yeah, this is the first line. I skip that. This is our base case is assume the v initial value it is 0, then it stops straight away. Yeah, if it's 0, it stops straight away. And if you have one to prove if it's n, and n plus 1 also stop. If n stops, n plus 1 also stop. I'm not going to give the precise arguing or the proof reasoning for this, but you can see the process. Yeah, process is just to do this from n. Assume n works, and if you prove n plus 1 must also work, then that's all your proof needed. So you can see why is induction important, because we can use this technique to do something useful. Yeah. Another thing is induction actually is used in our programming. Yeah, when you do programming, most cases you can use this technique to code your program to solve things. I'm not sure if we still have plenty of time. Okay, let's say this example. Yeah, the factorial. So we try to define factorial. We know what does it mean, n factorial. Yeah, n factorial means n times n minus 1 minus 2, etc. So down to 1. So that's the definition. Okay, the definition. Oh, why this is kind of some rubbish there? Okay, doesn't matter. Ignore my last line. So this you can actually be programmed into this piece of code. Let's just read it through. Yeah, can be in any language, Java, C. I don't know what other language you learned. Yeah, and any language, just slightly different syntax. We can write down this. So the function, the type of function. I think in Python they don't care about type. But if you really get used to C, C++, Java, so you have a sense of okay, what number, what object you look after here. It is integer. So you define a type is integer, and input is n. You want to return, yeah, n's factorial. Yeah, so in this code. Then what we do is we just have a if statement. First of all, we check if n is basically if n is 0. Yeah, it said less than equal 1 is we extend our factorial definition is if you gave me a wrong number, give me minus, we just say we just simply return 1. I'm not sure. You have to look up a definition. Yeah. Anyway, so another way to write this, you can just say, I think the better way. So make less confusion. Just change the condition. Say if n equal 0. That probably I think better to replace this. Yeah, it's the same thing actually. Same thing we want to do. When we just want to say in the base case, if you gave me 1, yeah, if you gave me 1, 1's factorial we know is 1. No computation involved at all. So I simply return 1, finish that function, finish this program. Yeah, I like to call the function. Yes, function will return n factorial. Is that clear? So that's your base case done. And tricky thing is here. Next line. I just regardless whatever is, I just say I can return. It's guaranteed n is number you gave me. Yeah, whatever n is now is definitely greater than 1. It's a number greater than 1. It is integer. And I simply return n times. And times product, yeah, do the times is okay. Machine is built-in machine. Your program understand how to do times. Yeah, and the next thing is I call factorial. I say factorial n minus 1. What does it exactly mean? Is this? Look at this formula. Do you agree? By definition, when we define n's factorial, you can just say n's factorial is actually n times n minus 1's factorial. Yeah? Are you happy with that? So let me just copy here again. So n's factorial, if you want to work out that, I say, okay, I'm not writing like this. This is too long. This is not maths. Yeah? I write it down in an inductive way. I will say n's factorial is n minus 1. Sorry, I put it in front. If you tell me what, assume I already know n minus 1's factorial, and then I just simply times n. Sorry, it's order different, but we know in multiplication doesn't matter order. Are you with me? So we base on this. This is inductive definition, inductive rule for generate any numbers factorial. Yeah, so I just put that into my program, and then you can see the factorial here. Factorial, this name appeared here. It's same name. Okay, I'm trying to define factorial n, but then inside my code, this is my code defining factorial. But then I'm allowed to just use that same function. I call myself. Okay, this is something we're going to talk a bit more next week. It's called a recursion, recursive programming. It's in the code, in the program, you call yourself. So you back call yourself, but be careful. I call it with a smaller number. Yeah. If I call it n plus 1, call bigger number, you will fall in the loop. You will, because you never reach your the final the base condition. Your base is 1 and is 0. Okay. So anyway, just quickly use this example to show you inductive definition is heavily used in computer science. And that actually turned out the programming technique we call the recursion. Okay, I'm not sure on my next slides. Yeah, there's another. I'll try to convince you why the induction is important. Give you another an example. This actually also to do with programming. I don't know why we got this thing modeled in the bottom. I can't see the program properly. Anyway, so let's go back to this example. We learned that there is a data structure called list. Doesn't matter if you haven't learned this, but it's just a common sense of a list. Yes, a list is just a sequence of items you put together. So order does matter. So you list who is front, who is back. It's different from set. Set we don't count about position, but list is element put in it 1, 2, 3 is in a different position and it's fixed. So So now we define, I want to define what do we mean by, of course, the list can be any order, yeah, anything. But you can say, I have a kind of special list, which is called ordered list. Okay, so this list is ordered by, from left to right. The number is guaranteed getting bigger. In this case, yeah, it's ascending order. So now let's come to definition. You try to give definition. Well, giving definition is good thing. Not only define what you say, also definition will give us a rule, a set of rule to tell you how to generate such information. Okay, you go back to, jump back to a natural number. So if you have a definition of a natural number, and you can write down this in your program, and you can guarantee it, allow this little engine program to generate any natural numbers, because it can follow your rule to go again to generate all the natural numbers. And here is also same thing. We're asking you, how can you define ordered list inductively? Okay, so we will again, say, no worry. You might think, okay, ordered list is you just say everything next to you is bigger than the current one, bigger equal current one. Yeah, so this is every neighborhood in your list, you should guarantee your next one, because the number is getting bigger, so your next one should be bigger, at least bigger or equivalent on your value. That's something you want to say. So you want to say that inductively, okay? So we're just giving these two rules again. So one is basis, second one is induction. Then what is basics? It says, if list only have a single number, okay, then it's guaranteed it's ordered. Yeah, so you just yourself, you're nobody to compare with you. So whatever your value is, millions or zillions, is ordered. Are you happy with that? So that gave you a definition. But now I look at back, I think that I want to add it to this diction. To saying you should also say empty list. Yeah. So if you give a list, has got nothing in it. Yeah, but at the moment, it doesn't matter. Let's say just assume we don't worry about empty list, but really empty list is also ordered list. It's better to start from empty. But anyway, forget about it. Just start from one element. Yeah, and then from there, what you can do is you can take the first element, the very first element in the list, take that out. Okay, and then you look at the remaining list. So you know the technique here for induction is you always prove from n to n plus 1. Yeah. So here I gave you a list. I gave you a long list. Let's say you have a long list here. The length is let's say this length is n plus 1. And if in order to prove this long list is ordered, I chop it into another two parts. So this is another list with length of n. So the n element is remaining. So I use this, we call it head and tail. So tail x will return you the remaining list by removing the first element. So your first element is here. Let's call it x is my first element in my initial list. So now the technique here is, if you can tell me the tail of that list is ordered. Yeah, so if you can, just let somebody already help you down all the hard work. So saying, okay, so tail of that list, the order, don't worry, but I have another extra thing in front, which is x here. So how can you prove entire whole list with x adding in front is also ordered? How can you convince yourself that is the case? Easy. You just take the first one from here, from your tail of list. Yeah. So all you need to check. Let me just change color a little bit. Don't know. Change to blue. So all you need to check these two. Because the rest of the thing all sorted. By assumption, you know the entire whole remaining list, they already ordered, yeah? So you just want to say that the joined part, the first value, let's call it that is y, yeah? We don't know what is called y. So the first one in your tail of list, if that is greater or equals to x, then the remaining thing you don't need to prove anymore because you know that's ordered anyway. So you just need to check the joined part. This is joined part, yeah. So I'm not sure why my slide is really not very good. Let me see for my next. Yeah, okay. This slide probably is better. Yeah. So you can write a program like this, saying. Giving a list, yeah. So input is L, can be just any list. Then, yeah, I think here I changed my mind. So instead of saying single element, I just say if it's empty, yeah. So if that list is empty, nothing in it, alternatively you can add another condition, yeah. If list have a single element, it doesn't really matter. But this one just works as well. You just simply return true because empty list is ordered, done and dusted. Then next thing is really interesting. You just take, okay, say the head of my list, yeah, in my previous slide is this one. Where is it here? It's this value, yeah, head of my list. And compare that the head of a tail list. Head of your tail of list is here. I compare L, head of L, and head of tail of L. Yeah. So as long as they hold this condition, then plus there's another AND. Yeah. This is logical AND. Then suddenly here I will say the tail. Can you see that here tail L is also ordered. Okay, I leave this piece of code to carry on to checking tails. Okay, this is not just a come out of blue. The God have the magic way to help you solve it, but it is this one. This program, the code list, will go back to code this same code again. So you reuse that. That function will be called once depends on how long your list, step by step, going down. It will keep checking the tail of list if it is the same. Basically, the go down, you check another one, go down, check another pair. Eventually, you go down until that list down to 0. And then they will return value back up. Eventually, all the neighborhood will be checked by using this, we call it recursion, yeah. But then here is actually, at this stage, we don't call it recursion. It is inductive definition. Okay, I hope this by using so many examples, but then later example maybe it's a little bit too much. I hope you guys can understand. So we just like quick summarize why is induction important. We use it to prove the correctness of your code, and we can use it to write program. That is recursion, and then the recursion program is more elegant. You can tell it's really very elegant style program, and then we can use this to do a mathematical proof. So this will lead to I can pre-announce a little bit on our very last piece of worksheet. You already see worksheet 4. Yeah, I put it on Blackboard. You finish it. You can finish it in two weeks, or a little bit more than 2 weeks. Plenty of time. And then my last one, I won't publish it until probably a few more days, maybe next week or next week. In no hurry. You can do it, which is I gave you some problems. I ask you to solve the little problem by providing 2 different style of program, either using iteration which is no recursion, basically just using loop structure, yeah. But using recursion, which is no loop. Okay, so I just want you guys to taste a difference between these two different style program. It is huge difference, yeah. Anyway, so that is a little bit something pre-announced. Okay, we have to now just remind you, warn you this. Induction, yeah, when you do the induction, although you see, I said it jumped from n to n plus 1, yeah. So we have to be careful. There's sometimes you don't use correctly. You might end up with something wrong. So here is like, it's a bit confusing, yeah. So let's just I try to confuse you, and then you say if you guys can get out from this confusion and then understand the concept a little bit better. And here is the way I try to do in induction, and I say, okay, assume person X, yeah, he gets the same exam mark as herself, or himself, yeah. So if I say I'm person, I get a set of exam mark. Surely, if you compare with my exam mark with myself, then it's same, yeah. You compare two same people, and then nothing wrong with this, yeah. Nothing wrong with this. You compare X with X. Yeah, X with X always get the same exam result. As the base case, you can say that. And then suddenly, I jump to this. Say if n people, just assume if a group of n people always get the same exam mark, if that is true, okay, if that is true, I just use induction, surely, doesn't matter. I add another person, I should also get same thing. So I say, so do n plus 1 people. So you have to really, I think in commons, it doesn't make sense, yeah. Doesn't really make sense. Well, you can make assumption. You can assume n people always get same result, that's okay. But if you suddenly move to n plus 1, then this step between n and n plus 1 is something need to be proved. So really, you have to prove that, yeah. You have to provide proof, and here it's very rush. You just say, okay. So I just assume if n works, why not 100 and 101? It's not big deal. You just assume the same. That's a bit vague, yeah. Yeah. So and here the argument, but if n is 1 is true, so basically that's reason is this, yeah. If n is true, so is true for n plus 2. N equals 2. I think this is a problem here. Yeah. N is 1, n equal 1 is true because you compare your mark with yourself. But really, you can't assume suddenly get another person. This 2 person has got same mark. There's no evidence. Okay. So really, as base case, this already break. Okay, so really there's a lot of holes in this kind of reasoning. So therefore, you get silly conclusions saying everybody gets same mark, but that looks like he's trying to use our fashion, the way we're talking things, yeah, especially this description like this, but actually it's not, yeah. This is, we call it bad example. Okay, that's a little exercise I want you to do in tutorial. Yeah, there's more. This is all today's tutorial, today and tomorrow, this week's tutorial. So please do go to your tutorials, and you will do a lot of exercise on this. That'll be really useful. Yeah, and here those code. I think we can skip this code. I come back if I have a time. I do it next week. And this again, yeah, this is entire whole program. Well, no program, just a pseudocode to do comparing 2 strings. Compare if 2 strings are equal or not. And you can see if you read my code, I'll read my algorithm here. You can just see the difference. The way how you define things. It's, I think, really, I think should be quite eye-opening things, because this is totally different way to do repeated computation. So far, we do repeated computation. We just simply use a loop. You create a loop, do something a couple of times, and it seems like example here. When you try to compare two strings giving in, I don't need a loop. It's a no loop, okay? I just saying if they're empty, I start from empty, If both empty, surely they're the same. Then you just return truth. And otherwise, what they do, they just say, I compare the first element. I just take first element from two lists, check if they're same. If it's not same, the end of story, they're not same anyway. But if they're same, and then also check the tails of both lists, they are same. And this is just through our inductive technique. I just say, okay, as long as you prove me the tail of list also same, and plus one, I just done for the head part, two head the same, and you check tail. I just authorize the next task to a remaining program saying you do this bit, okay? But then that's what the remaining thing will use the same logic, using same algorithm, come back to check if you're empty. If you're not empty, I do the tail. If you're not empty, I check head. So that head will be the second element, and so on and so forth. You basically step down, eventually you dig down. If they're both same, you reach empty, okay? And then they will eventually return true. Anyway, so that is the way, more example here. You can also thinking about define a length of string. It's a lot of little things you can do. So that's pass. And another thing is, okay, let's go back to do worksheet 4. Okay, let me just stop here. Maybe just check you guys. Do you have any questions? Do you have any questions regarding today's inductions topic? Can we have a few minutes for the in-class test? But again, because I open in-class test, today's in-class test is always open until the end of today. So if you want to do it now here, it's okay. But if you think you're a little bit too overloaded, you can do it later. When you go back home. So we have in-class test. Next week we carry on. We move to a little bit more recursion. Any questions? Any quick questions from you guys? You all understand, so you all follow. Okay, so hope you go to tutorial, do some more exercises. And next week we'll do more. See you next Monday.